Okay, today we're talking about geometry and trigonometry and a few things related to that. International mindedness. The word sine comes from the Greek word sinus, which means fold, or derived from the Indo-Persian Arabics for half chord. They are used all over the place. Um, we will look at relationships between trigonometric ratios and identify equivalent expressions to form really basic identities. We do not go very deep into identities in this course. Um, Theory of knowledge connection. The concepts in this section rely on what is called a perfect circle. Does perfect circle exist in nature? If you said yes, you may need to read the article from Carnegie Mellon. If perfect circles do not exist, then how could mathematics focused on geometry of circles be said to be valid? Um, Must knowledge, so knowledge question, must knowledge have a real world corollary in order to be valid knowledge? An interesting question to think about and debate. Okay, now we move on to the unit circle. Okay, within a circle, there is symmetry. I can draw this point here, and it will be negative 0.6, 0.8. There is one down here, negative 0.6, negative 0.8. The key to the unit circle is this radius here is 1, and these are all triangles. Coordinates are your lengths. There's one down here, 0.6, 0.8. And as we get to the unit circle, the x coordinates on the circle are the cosine of x. The y coordinates on the circle are the sine of x. No, actually, I should call them the sine of theta. The angle is theta. It is measured to the positive x-axis. And we'll use theta so it's not confused with x and y coordinates. Okay, very important things to note about the unit circle. If you can develop quadrant 1, you can develop all these other quadrants using reference angles. Theta would still mark to the positive x-axis, but this reference angle would create the same triangle inside. You do not get a unit circle on your IB exam. Might be helpful to have it memorized, a lot of which you can do with your calculator, but still not a bad idea to have this thing memorized. You need to know the four quadrants. So, given that cosine of 57 equals this and sine of 57 equals that, draw a unit circle and label 57. Okay. Draw an inscribed rectangle in the unit circle. Okay, the vertices are then over here, negative 0.545, 0.839. Use the symmetry, so I'm doing that. Use symmetry of the rectangle to determine angles. So if this is 57, that's 57 there. I can subtract that from 180 and get 123. I can add 57 to 180 and get 237. I can subtract 57 from 360 and get 303. And then this is to complete the table. That's showing all the rest of them. And notice the signs, the cosine is positive in quadrants 1 and 4, negative in 2 and 3. The sine is positive in 1 and 2, negative in 3 and 4. So this is where x coordinates are positive, where the cosine is positive, y coordinates are positive. Oh, there's this relationship. Um, so copy the diagram. It wants me to mark theta minus, or pi minus theta. Pi minus theta, pi being 180 degrees, this being equivalent to theta. This is pi minus theta. 2 pi minus theta is going to be down here. So those are the first two in this example. Really important to be able to draw these things on the diagram. Pi plus theta and theta plus 2 pi. Okay, theta plus 2 pi. 2 pi is a whole circle. Theta plus 2 pi is this. Pi plus theta. Now it's going to go all the way around. Theta plus pi or pi plus theta, doesn't matter. And this allows me to get all angles that have the same reference angle within one or multiple unit circles. Notice to add a unit circle or a circle, you just add a 2 pi. Make sure to always get common denominators because a lot of radians are in pi over 3s or pi over 7s or... Okay, so if sine of alpha equals 3/5, I'm going to draw this on a circle. Yes, this circle is radius 5. The measures are still the same. So that's alpha. This is alpha. This is pi minus alpha right here. Just like we did in the last one. 3, 5. This is going to be, these are 4, 3, 4, 5 relationship. That's -4. But that doesn't really matter. So that's -3/5. Or no, that's not -3/5. That's still +3/5. The 3 is positive. Now pi plus alpha. Let's just do this in a different color. And I'm just going to add alpha here. Now my 3 is negative. My 5 is still positive. This is -3/5. And like before, 2 pi minus alpha. -3, 5 on my triangle. Not a very good drawing here, but -3/5. And that matches up with the signs. Signs are positive in quadrants 1 and 2, the given in A, negative in 3 and 4, B and C. So now, important information. This tells us that this is it's an acute angle, which tells me it's in quadrant 1. If the sine is 2/7, this is 2/7. I can use the Pythagorean theorem. And when I solve that, I get square root of 45. So the cosine of this angle is square root of 45 over 7, adjacent over hypotenuse. When I'm doing my angle here is called x for this particular one. 3 pi, 2 pi is here, 3 pi plus x is going to be down here. So my triangle goes this way. Whenever I do a hypotenuse, hypotenuses are always positive. The x is going in the negative x direction, so it's negative square root of 45. The y is going in the negative y direction, so it's negative 2. And we get those. Okay, tangents using the unit circle. I'm told sine is 1/2 and my angle, okay, this tells me my angle is between 0 and pi over 2. That tells me it's quadrant 1. Sine is 1/2. That's going to be square root of 3. Okay, tangent of x, 1 over square root of 3. In this course, you don't necessarily have to rationalize, but to rationalize, you multiply by square root of 3 over square root of 3, which gives you square root of 3 over 3. Okay, tangent of pi minus x. It's going to be over here. Again, negative 1 over square root of 3. And pi plus x down here. So now I've got a negative on both of them. So that becomes positive. So it's negative over negative, or 1 over square root of 3. And that's the end of this section. Exact values on the unit circle come from the 30, 60, 90 and the 45, 45, 90 right triangle. So find the exact values of 7 pi over 6. So 7 pi over 6 is pi plus pi over 6. Pi over 6 being a 30-degree angle. 30, 60, 90, so 2. This is down, so it's negative. This is also negative. The sine being, I always use this reference angle to the x-axis when I do this. Alpha, negative 1 over 2. Tangent being 1 over square root of 3. Oh, they gave me a different cosine. Cosine of 5 pi over 3. 5 pi over 3 is here. It's pi over 3 less than 2 pi. Pi over 3 being like a 60. That's 1. This down part is negative square root of 3. This is 2. Cosine is 1/2. And you can check your unit circle to verify those. The key, creating the unit circle, if you have the 30, 60, 90 and the 45, 45, 90, sure that's actually 1, but the ratios stay the same. So if you know these, you just have to bring them around the circle. 30 being equivalent to pi over 6, 60 being equivalent to pi over 3. And yes, you do sometimes have to change them. Flip that around. You have to make it fit as you go around the circle. This is used when we do the law of sines. So we have the ambiguous case of the sine rule, which is the side-side angle case. Side-side angle is not a congruence theorem. And the triangle they drew here, there would be another one with a 7 there. So it creates two cases. So in the triangle shown are possible values for B, C, and side AB. So it wants me to find angle B, angle C, and side AB. So the first thing I'm going to do is I'm going to find B. I'm going to use the law of sines. The law of sines says sine of 30 over 7, I'll side across from it, equals sine of B over 12. And when I solve this, I multiply both sides by 12, and then I do the inverse sine. I go to my calculator. I make sure it's set in degree mode because I'm doing degrees here. I type it in. And I get 58.99 degrees. So 59.0 degrees. That is case one. We're going to finish solving this for this triangle here. That's the acute angle. The sine will always give you the acute angle. This I can get by doing 180 minus, which this is going to be 91 degrees. My side there, I'm going to use the 30 because it was exact, not, even though it's 59.99 that, or 58.99, that's very, very close to 59. I'll still use the one that was exact. So I'll cross multiply. And then I'll divide. And I get a length of 13.99 or 14.0. So that's case one. That's possibility number one. Possibility number two involves this. And if I knew this was 59.0, I can do 180 minus that. So this is 7. This would be an isosceles triangle. That's 59.0. So my inside, these are going to add to 180, 121, making this 29 degrees. To get my other side, I can do sine 29 over, call it x, equals sine 30 over 7. I'll multiply by 7 and I'll cross multiply And then I divide by sine 30. And I get 6.79. And those are my two cases. Okay. That is the ambiguous case, the side-side angle case that happens with sometimes, and we can solve for the two possible triangles with the law of sines. The key is this little isosceles triangle here and the 180 minus to get the angle. Um, Go ahead and read over the international mindedness box and talk about the Pythagorean identity. So, the Pythagorean identity, the most basic identity, and I'm just really annoyed at this triangle, so we're going to cross things out. We're going to call this C, we're going to call this C, and this B like a normal right triangle does. The Pythagorean identity, which I'll prove in a second here, is sine squared theta plus cosine squared theta equals 1. We have the other forms where we subtract cosine squared from both sides. Or you subtract sine squared from both sides and you get this. Or what if we decide to divide both sides by sine squared? Which is 1 plus cotangent squared theta equals, oops, that's not 1. I don't know why I wrote that like that. Dividing everything by sine squared theta, which would give me cosecant squared theta. And you can rearrange this like we did the ones above. Or if you divide by cosine squared theta, you get tangent squared theta plus 1 equals secant squared theta. All different versions of the Pythagorean identity. So I'm going to prove this from the Pythagorean theorem. Let's call theta this angle here, angle A. That means sine of theta equals A over C. Cosine of theta equals B over C. So that means sine squared theta, which means I'm just squaring my sine. A over C squared, or A squared over C squared. And cosine squared equals B squared over C squared. So I start with the Pythagorean theorem. That's been proven. I'm not going to prove it here. You can take my word for it. Or, every other math book in history's word for it. And we'll divide everything by C squared. And then we get A squared over C squared plus B squared over C squared equals 1. A squared over C squared is sine squared theta. B squared over C squared is cosine squared theta equals 1. Thus it is known as the Pythagorean identity, and it works great. You do not do very much with these identities, but it's important to know them. Once in a while, you'll have to do something with them. Okay, so we're going to look at these two examples. Find the exact value of cosine alpha if sine alpha equals 1/3. No, you can just the exact values. You can draw this out and get this is square root of 8. Sine would also equal it over here. So it's plus or minus square root of 8 over 3. You can also do so doing cosine squared plus sine squared plus 1/9 equals 1. 8/9 square root both sides. And you can split the square root. That's an important property. So I square root 8, and then I square root 9, and that's 3. The next one looks like a pile of garbage because it's got typos in it. I looked at the answer, and it's supposed to say this. So 1 minus cosine squared is sine squared. 1 minus sine squared is cosine squared. Sine over cosine is tangent, so it's tangent squared theta. That's some basic uses of the Pythagorean identity. Um, Now we're going to show you solving a trig equation. You will only solve trig equations with your graphing calculator in this class. That makes your life easier. So we have this trig equation. 3 cosine x equals tangent x for x from 0 to 2 pi. So it wants all the solutions in that interval. So we're going to go grab a graph. We'll type in 3. You can type it or you can use the cosine button, but since I have a normal full keyboard, I just decided to type. Oh, when you type, you must have parentheses. You know what? This is being a pain. We're going to start with a new one. When I want to use the cosine function, I must put parentheses in it. Looks like that. And my other side of the equation is just tangent of x. Now, because it gave me an interval, I'm going to set my zoom, my window, my x-min to be that. My maximum x was 2 pi. And solutions are simply where does it intersect? So I've got 2, 1.011. So it was asking about x. So all I needed for my answers are my x coordinates. But I should probably get my other one. 2.131. Okay, and that is the end. So this is useless. That is the end of section 3.8.